Start the recording. All right. Boy, attendance has dwindled a bit. It's fine. Um, my standard set of course announcements, as always. Um, problem set 5 is out, has been out. It's due tonight. So please make sure to work on that. The second programming assignment was due a few days ago, but the late due date is tomorrow by midnight. So if you haven't already turned it in, or if you're not quite happy with the grade that you got on it yet, and you want to use some late days, feel free to turn that in as well. Standard reminder that there is a write-up portion that you can do for up to 10% extra credit. I have so far caught up with all of the write-ups that have been submitted, but you can feel free to submit a write-up until the late due date of the program assignment. And there's no like late penalty or whatever on the write-up. So even if whenever you submitted your code, you can submit a write-up and get up to 10% extra credit on that. I will hopefully be releasing problem set 6 sometime today or possibly tomorrow, depending on how long it takes me to write it. But it's going to be mostly about graph theory stuff. It'll be about graphs, graph representations, stuff we've been talking about in class the past couple of days. As a reminder, the final exam is scheduled on my Purdue. I think it says it's 2 weeks from today. Instead of having it be like an in-class thing where you sort of show up synchronously and you're proctored and take it on Zoom and stuff like that, I think I'm going to make it a take-home exam. So be on the lookout for some more details involving that, but chances are you'll get a PDF or something like that of the exam on Wednesday. You can sort of take it at your own leisure and submit your solutions to Gradescope. By I think the latest I can make it due is Friday, but if I can make it due like that Sunday, which is technically 2 days after class ends, I will do that. So be on the lookout for that. And the final exam will be cumulative. We'll talk more about that, or I'll give you maybe some more details when that gets closer. But yeah, one of the fun parts of having an 8-week semester is we get a final exam almost immediately after the midterm, which is great. I love it. All right. Any questions on logistics before we jump into content? All right. There's nothing on a new whiteboard. Okay. Here we go. All right. So make sure there we go. The past few lectures, we've been talking about graphs. I feel like I start every lecture by writing graph at the top, or writing graphs at the top of a whiteboard. Today is certainly not the day I break that habit. So we've been talking about graphs. We did a bunch of definitions. We talked about representations. We talked about, so maybe I'll say, talked about representations. We talked about DFS and BFS, right? And then yesterday in lecture, we talked about topological sorting. We talked about 2 different methods for topological sorting. One was DFS. We'll sort based on finish time. And the other one was this thing called Kahn's algorithm, which basically greedily grabs available vertices to schedule. Right. Remember, this one obviously has DFS vibes. This one sort of has BFS vibes because we're kind of starting at the top, grabbing all of the children that we can that have an in degree of 0, and then kind of recursing on their children and so forth. Before I move on, so that is about all I wanted to say about topological sorts. So in particular, today's lecture is not going to be about topological sorts, which means before I move on to today's topic, are there any questions about graph stuff that we've talked about up until this point? So that includes definitions, that includes graph representations, that includes depth first and breadth first search, and that includes toposort. Any questions? Anything I can help clarify before moving on to new content? Let me ask this. How well do people, or how comfortable do y'all feel with topological sorting? Like if you had to implement one of these yourself, or if you had like exam questions about topological sorting or something like that, how, I don't know, maybe on a scale of like 1 to 10, how good do we feel about that at this point? You could do a homework problem on it. Okay, that's good. That's actually very good. You likely will have to do a homework problem on it. So, all right, cool. In that case, I feel even better about moving on. Today, I want to talk about shortest path algorithms. In particular, um, there's sort of 3 algorithms that I want to talk about. 2, maybe 3. We'll see. We'll see what it ends up looking like. The first one is Dijkstra's. The second one is called A star. The third one is Bellman-Ford. So for a bit of context, Dijkstra's is sort of like, in my opinion, the most important one here. A star can be seen as a generalization of Dijkstra's. Or maybe another way to say this is Dijkstra's is sort of a special case of A star. And then Bellman-Ford is sort of its own thing. It's useful in almost like a disjoint set of circumstances. So you kind of, yeah, it also computes shortest paths, but it does so in a different way and under different circumstances. So what I thought would be fun for today's lecture is maybe we can try to sort of independently rediscover Dijkstra's algorithm, right? And then once we have that, we can maybe try to see if we can extend it easily to A star. And then if there's time at the end, we'll talk about Bellman-Ford. But these are sort of the 2 important ones that I really want to get to. That sound good? I guess you don't get much choice on whether that sounds good. Um, I don't plan on making a new lesson plan just because one of you says that doesn't sound good. I don't know. Uh, okay, so let's think about Dijkstra's. Um, the the setup here is we have a weighted graph. Maybe I'll say a weighted directed graph, where V is a set of vertices, E is a set of edges, and W is a function that maps the weights of edges to, for now, let's say real numbers. Um, we have a source vertex, which is an element of V, and we want to compute the shortest path to all other vertices in the graph, right? So in particular, we're not starting with a single source and a single target, and then trying to find some path that goes here. We're starting with a source and sort of everywhere else trying to figure out what the shortest path looks like. I am so bad at drawing, so I'm not going to try. But yeah, this bit is sort of important, right? All of the vertices. Does the setup of Dijkstra's make sense? Maybe you can start to see how this is like something you might care about for your programming assignment. Well, of course, in the programming assignment, instead of real numbers, the weights take values in like lists of, I think I said lists of integers. Um, but hopefully, we'll be able to talk about how you might model that as a as an easier graph problem, or maybe you can think about that. I don't know. I think it's cool that you have to think about things for your programming assignments. Um, okay, so the way I want to approach this is essentially like one big exam problem, right? So uh, in particular, maybe um, maybe I'll give us a starting point and say that we're going to use dynamic programming, right? In fact, Dijkstra's is sort of what you get if you think about the like naive way to do the naive way to solve this problem, right? The naive way to compute the shortest path to every other vertex, and um, then try to apply dynamic programming and sort of figure out a good like bottom up schedule. Um, okay, so this is going to be very interactive in particular. Like, or this portion of the lecture, I am hoping to make it very interactive because I really want you all to sort of tell me how to write pseudocode for Dijkstra's or how to write pseudocode for computing all of these shortest paths, and then how we can apply dynamic programming and that sort of thing. Um, Maybe to motivate you to pay attention. We'll say the attendance poll is related to this. The attendance poll for today. How does Dijkstra's compare to a simple breadth first search, right? Um, if you remember from lecture on, I don't know, Wednesday, we talked about right breadth first and depth first searches, and we talked about how, in particular, a breadth first search orders the vertices it traverses in order, in increasing order of distance from the source, right? So in particular, you might think like breadth first search already kind of gives you a shortest path, right? So why do we need Dijkstra's? And it turns out there's a good reason for that. There's a good like sort of failure mode for PFS that I've kind of implicitly hidden in this problem statement. Um, and that is something that will hopefully make sense by the end of this lecture. If not, we can talk about it explicitly, or you can give me your best guess. We'll probably talk about it explicitly. That's fine. Okay. So does everyone have that as the attendance poll? Because I'm going to move on. Okay. So all right, let's do this. Normally, when we formulate something as a dynamic programming problem, right, we've done this on problem sets. We did this on a problem set with the sort of like matrix chain multiplication thing. We did this in class with the rod cutting example. Um, and we did this on the exam. I think I can say that now because everyone's taking the exam. We did this on the exam with with edit distance, right? Um, so what are the sort of like uh, maybe shout out in the chat. What are the steps of coming up with a dynamic programming algorithm? Right? What are the steps that we want to take right now? What's the first thing we do? Okay, base case. So yeah, let's say base case. Base case is really sort of a sub step of what I'm thinking the first step here is, but that's fine. We can expand it out. So come up with a base case. The problem on edge vertex from the edges of the starting point. Well, okay, let's not get specific yet, right? So just in general, when we're building a dynamic program, or when we're building a dynamic programming algorithm, or when we want to use these techniques to like design an algorithm, right? The first thing we want to do is figure out the base case and the inductive case, right? Basically, design a naive recursive algorithm, right? This is what you've done on your problem sets. This is what you've sort of done on the exam. This is the way we've approached it in class, right? So you look at the naive recursive algorithm. Then we, I don't know, maybe convince ourselves that dynamic programming is helpful or even possible, right? This part usually entails thinking about the number of subproblems, thinking about how like whether solutions to larger problems contain solutions to smaller problems, and thinking about like the overlap, right? Actually, I guess that first part is like thinking of it as a recursive algorithm. But we convince ourselves that dynamic programming is helpful, and then we uh, um, right, we compare the top-down memoized algorithm to a good bottom-up schedule, right? In general, these are the three steps, right? So we figure out what we sort of we get something that's correct first, right? So sort of just like, this might be enumerating every possible path and then um, the shortest ones. Of course, that's easy to say, but we sort of formulate this as a nice recursive problem and kind of convince ourselves that like right, larger subproblems contain solutions to smaller subproblems within them. Um, then we enumerate the actual subproblems and think about what it means to like share work between them or like reuse smaller results. And then hopefully, if it seems like that might be helpful, if it seems like there's way more uh, if it seems like the recursive algorithm is doing way too much work compared to the number of subproblems, we try to tabulate, right? And so we build like a table that sort of uh, monitors every possible subproblem and kind of deals with that, or like records the results on every subproblem, right? This is a sort of general approach for doing dynamic programming. Let's start with a naive recursive algorithm, right? Actually, let's start with convincing ourselves that a naive recursive algorithm is possible. Okay. So for a recursive algorithm to be possible, we need to subdivide the problem and have, or maybe I'll say like a guarantee of correctness, right? So what does a subproblem here look like, right? If I've got a graph, maybe this is my graph. I don't know. That looks like a good enough graph. And maybe this is my source vertex. Right? So if I've got a graph like this, um, naively, I have to think about every possible path through this graph that starts at S, right? And maybe I've made this too nice. Maybe I should maybe I should mess this up a little bit, right? Throw that in there, give it a nice cycle. Um, maybe flip the direction of this edge. There we go. That's a bad graph. Um, yeah, okay. So um, yeah, okay. I guess what do my problems look like, and what do the sub problems there look like? Any thoughts? If you have to search for a specific vertex, the only thing we can do is visit every outgoing edge. Yes, we do need to visit every outgoing edge. In particular, we need to visit every possible path, right? From the source to any other vertex, right? Now, in particular, let's say for each v in v, we want the shortest path from S to V, right? Um, for a problem like this, the shortest path is going to have some length, right? It's going to contain some number of edges. And maybe we can think about what a subproblem here looks like. Any thoughts? If I happen to know the shortest path from, let's say, like, uh, if I have a graph, and here's S, here's a bunch of vertices. There's other stuff going on in this graph, and here's my target vertex V, right? Right. There's other stuff going on in this graph that I'm not drawing. I'm gonna make this symmetric. If I happen to know that this is a shortest path from S to V, what other information is contained inside that statement, right? The fact that this particular sequence of vertices going from here to here to here to here to here, the fact that this particular sequence of vertices um, is the fastest way or the shortest way to get from S to V. What else does this tell me? All right, the thing that we care about, if you remember from like week 2 or 3 or something, is if we want to formulate something as a recursive optimization problem, or if we want to formulate like an optimization problem as a recursive algorithm, then we need to know that a an optimal solution to a big problem necessarily restricts to an optimal solution to a bunch of smaller problems. Um, was that also the shortest path to each of those vertices in between? Exactly, right? So if this is the shortest path from S to V, then it must necessarily be the shortest path from S to, let's say, this vertex in the middle, right? Because if there was a shorter path, then we would get a shorter path from S to V just by taking that shorter path, right? So we know that a shortest path, let's say, shortest path, I'll say maybe S, like V prime to V, must restrict to a shortest path S to V prime, right? That's exactly it. And in particular, the path S to V prime is going to be smaller because it contains at least one fewer edge because there's something from V prime to V, assuming V prime doesn't equal V. Um, and so we get like a solution to a big subproblem contains solutions to smaller subproblems, right? Um, in particular, like this also tells us that like this is the shortest path between these two vertices, right? So it sort of gives us like the shortest path between any pair of vertices on this path from S to V, right? Because again, if there was something shorter, we could have um, we could have taken that shortcut and kind of bypassed it. Um, okay, so with that in mind, maybe by writing a uh, we can start by writing pseudocode for a recursive algorithm. Given a graph, given a source vertex, and I don't know if we'll use this, but let's keep a target vertex as well. Right. Yeah, actually, let's keep a target vertex. Um, so given the fact that our subproblem is like the shortest path from S to T necessarily contains the shortest path from S to something in between, right? Um, how might we go about doing this? So first of all, what's our base case, right? Anyone? If S has no outgoing vertices, return if S has one outgoing vertex, then the new S is that vertex. So this seems iterative, right? Um, Robert says the shortest path from S to an adjacent vertex. Um, Possibly, but consider like, unless I'm misunderstanding what you're saying, consider like S to T, this has a weight of 100, and there's some like U here, which is like 5, and then a 5, right? Even if even if T is adjacent, it might like that single edge might not be the shortest path, right? What's the case? Like what does the graph look like when what does the graph need to look like for the shortest path problem to be trivial, to require no computation at all? S is T, thank you. So if S equals T, what do we return? 0. Yeah. Um, right. Maybe this we want this to be like the sort of length of the shortest path. Right? Yeah, we could return a sequence containing just S, or like we could do this, or we could do like um, the empty set for the fact that there's no edges, however we choose to represent paths. Um, but legendary char star star, I don't array of string. Okay, I don't know. Sometimes there's references that I don't get, and that's okay. Okay, so if S equals T, we know that the length of the shortest path is necessarily 0, right? Of course, there's this like we could have something stupid, right? Like an edge here with a weight of -10, right? And then the length of the shortest path is -infinity, because we could just keep taking this -10 edge, and then it's broken, it's busted. So ignore that, right? If S equals T, return 0. Um, Now that's a good base case. What's our inductive case? This is where we sort of have to look at edges. Right? If S does not equal T, then we know we have to take at least one edge somewhere, right? We don't know which edge, but we can try every possible edge, right? So maybe I'll say for each edge from S to some other vertex V, for all edges, call shortest path and store the minimum. Yeah. So okay, let's try that. Adds equals maybe an empty list, and then um, or maybe I don't know. Maybe let's make this like a dictionary. Let's make it a list because we don't care about the um, we only care about the length, right? So for each edge from S to V, um, what is the recursive call you want me to make? And we'll say like pads dot append. And it'll look like shortest path. What are the parameters of this recursive call? GVT. All right. And then I can return the min pads. Does this look right? Do people agree? No, thank you. Thank you for disagreeing. What's wrong here? We need the weight of the first edge, exactly. So I'm going to do plus the weight of S arrow V. And I really wish I knew how to move things. Wait, can I? Oh, oh my God. Oh my God, is this it? Did we just crack the code? Game changer. Absolute game changer. Okay, cool. Yeah. So, um, yeah. So we recursively call shortest path, assuming that we're taking a particular edge, and then we kind of we add the weight of that edge, right? And then we return the minimum of all paths. Does this look right? Do people agree that this is the that the pseudocode is correct? This should be fine. Okay. Everyone agree? All right. If there's no disagreements, I'm gonna move on. Great. All right. So, um, we we convinced ourselves that a recursive algorithm is possible, and we wrote a nice recursive algorithm, right? So we did step one. I completely missed. Okay, we did step one. Um, let's do step two, right? Let's convince ourselves that dynamic programming is both possible and actually helpful. So at a minimum, what is the uh, what is the time complexity of this? How many calls to shortest path does this make? Or like how many times do we try to solve a problem? However you characterize literally every possible path from S to T. Mm-hmm. Infinite if it's a cyclic graph. Thank you. I was waiting for someone to say that. Yes, this is in fact still not correct because if um if we've got a graph that looks like, you know, S T U. So everyone, let's say S. I'm going to put a V here and then put a T here, right? So we're going to start at S. We're going to move on to V. We're going to look at the shortest path from V to T. Part of that is going to be looking at the shortest path from U to T, and part of that is going to be looking at the shortest path from S to T, right? So the shortest path from S to T is going to sort of depend on the shortest path from S to T. So this recursive algorithm is in fact not going to work. I mean, this pseudocode is not going to work. We need to remember visited nodes to avoid traversing them again. Yes, and in some sense, this is what the dynamic programming is going to do. So maybe infinite does not halt. Angry face. I don't know how to. Okay, all right. So the question here is like dynamic programming is useful if there are, I guess, in this case, a finite number of subproblems, right? Are there a finite number of subproblems? And if so, what are they? How do we characterize the subproblems? Shortest path from all vertices to T. Yeah. So there's a subproblem as to all vertices. Let's do it. Well, I mean, shortest path. I mean, it's kind of. I guess it's not symmetric. Okay, let's say as to all vertices, right? Um, shortest path. Right. We could have instead of sort of inducting on the left, we could have inducted on the right and said uh, for each v coming into T, then we could have done SV plus the weight of VT, right? So the sort of like recursive thing here, right? There's S here, there's T here. We could strip off this last edge and recurse here, or we could strip off this first edge and recurse here, right? Since we want to find the path from S to every other vertex, it's maybe better to recurse to strip off the last one, right, and sort of recurse on the left. But yeah, we have the shortest path from S to V, and so there are, we'll say, theta of V such subproblems, right? V is finite. Honestly, I mean, it's a finite graph, but even if it weren't a finite graph, like there would be fewer subproblems than every possible path, including cycles. So, right, you sort of have an injection from vertices into the set of paths. Um, I don't want to say more about that, but yes, dynamic programming is helpful, right? Are people convinced? I mean, maybe you should be because I've sort of the premise of the last like 45 minutes has been that we're going to use dynamic programming to solve shortest path. So, um, maybe that should sort of, I don't know, bias you towards thinking that it's going to be useful. Okay. So path line. Let's think about a bottom-up approach. I know normally we start with like memoization, we say top down, but we've sort of realized that like uh just like if the graph has cycles, then just like recursing on these cycles is not going to really give us anything. So um let's start with a top-down approach, or let's start with a bottom-up approach. Right. So the first step for a bottom-up approach is we initialize a table um, with like space for all subproblems. Right. And then we what's the word? We come up with a good schedule, and we need an update rule. Wow. We need an update rule. Please pretend that my handwriting is better than it is. Okay. So these are sort of the steps of designing a bottom-up approach, right? this is sort of what we've done. I guess normally I haven't had you write like actual pseudocode for this, but these are kind of the steps that you should be thinking about. So we need to solve every subproblem. So we have a table with, recording the results of every subproblem. We figure out the right order to solve these subproblems in, and then we figure out what a good update rule looks like. Right. So after we solve one subproblem, how do we use that to solve the next one, and so on. So initializing a table, this is easy, right? There's a subproblem for every vertex. So we just have an array. You know what? Let me actually draw a graph and let's like try to do this. So I'm gonna draw a graph. And just for fun, we're gonna have a cycle. I'll say maybe I'll start with like A, B, C. B goes back here. C goes to B, and then BC also goes to the target, right? And I don't know, shout out like 6 numbers, or give me a number, not too big. I don't wanna do math, but like give me an edge weight. 7, thank you. All right, give me another one. 3, give me another one. 10. All right, give me another one. 8, give me another one. 2, give me one more. 4, wonderful. All right, here's our graph, right? So we're going to start by initializing a table, right? For all of the vertices. So we've got S, A, B, C, and T. And what are the values that go in this table? Like what are the semantics of the values in this table? The weights of the paths. Yeah. So in particular the distance, right? So we know yeah, so this is a table of let's say shortest path distances, right? When we initialize this table, what do we initialize in here? Right. The initializing the table corresponds to the base case of our recursion, right? So um, I'll say maybe from S. The base case is, what's the base case? S to S, thank you. And what's the distance from S to S? 0, perfect. Okay, now, what's a good schedule? What's a good like order to visit these vertices in? Because that's the second thing, right? We've initialized our table, right? So now we need a good schedule. Given this graph. Anyone have thoughts, ideas, suggestions? Throw them out. we can, okay, so I see there's order in order of degree, adjacent nodes first, fill in what's available to S first, so the paths from A to C. Yeah. Okay, so let's try. I guess actually, Robert, I'm not sure what you mean by in order of degree. You mean like fill in nodes with a lower in degree or out degree? Perfect. All right. Yes. So we agree. Yeah. So let's start. This essentially corresponds to like a breadth first order, right? So we'll do like a BFS traversal. Why is everything slanted? I don't know. Here we go. BFS order, right? So we start at S and we do A and C, right? What's the what do we fill in for A? 7. What do we fill in for C? 8. Perfect. Okay. Now we're done with S and we've got A and C, right? So we can continue our breadth first traversal, right? And say, so I mean, BFS sort of puts these things into a queue, right? So we say like we've got S in the queue, we DQ S, we add A and C into the queue, and then maybe we start by DQing A, right? So now we've got B. What do we fill in for B? Oh God, this is like weirdly. I'm gonna replace this with a 4. Sorry, just for illustrative purposes. So, um, we've we've visited S, right? Now the queue contains A and C. So let's start at A and visit all of the adjacent neighbors of A. In particular, this includes B, right? What uh, what do we start by putting into B? B gets 11. Yeah, right? Because A is already at a distance of 7. We do that plus the weight of the edge to B. So B gets 11, and we put that in there. Now, here's where this starts to differ from a breadth first search, right? Is because now we look at C, right? C also has an outgoing edge to B and it has an outgoing edge to T, right? If we visit, like, do we still visit B, first of all? Normally in a BFS, we wouldn't, right? We would say, okay, B's already been visited, so we've marked it off, so we're going to skip it in our traversal, right? Must, because exactly, yeah. So in this case, even if we've already visited something, we still have to revisit a node when we're doing our traversal, right? So we revisit this edge from C to B, right? What do we want to write into this edge now? Or what do we update the table basically? And if so, what do we update it with? 10 is less than 11, so we rewrite this to be 10, right? Maybe I'll keep the 11 and I'll cross it out, right? Now we've and then of course we've got C to T, right? So now we visit this edge and we write a 12, right? 8 plus 4 is 12. So now we've visited S, we're done with S. We've visited A and C, we're done with those. We've enqueued B and T, right? Let's start with B. What are the outgoing edges from B? B only goes to S, which is visited, so it isn't considered. Ah, this is weird, right? Um, C had an outgoing edge to B, which was visited, but we still considered that edge. B to S, but it has a higher weight. Yeah. So what we do is we look at B to S, right? And we say, okay, um, if I were to take this edge, I would write 7 plus 4 plus 10. I would write, or not 7 plus 4, sorry, 10, right? The distance to B is 10 plus 10. So I would try to write a 20 here. But the thing is, I already have a better path to S, right? So if it was a negative weight, would we overwrite that, or is that nonsensical in a graph? Thank you so much for saying that. I will get back to this question in like 2 minutes. Um, yeah. So we try to write a 20. We notice that we already have something better, so we don't update it. And because we didn't update it, we don't put S back in the queue, right? Which is why S now only gets visited once. Um, so that gets rid of B from the queue. Now we look at T. There's no outgoing edges, so we're done, right? So we filled out this table, and this in particular tells us the shortest path, or the length of the shortest path from S to any other vertex. Oop, I crossed thing, whatever. Yeah, right? So we filled out this table. Of course, this doesn't actually tell us what the shortest path is, but we can do kind of what we did for BFS. And in addition to this, we store like a predecessor table, right? So S, A, B, C, E. And the predecessor here starts at null. When we write to A and C, we store the predecessors as S. When we write from A to B, we store its predecessor as A. When we overwrite from C to B, we replace its predecessor with C. And then we go from C to T and we write its predecessor as C, right? And so now if I want to know the shortest path from S to, let's say, C, oh, that's a bad example. If I want to know the shortest path from S to B, I say, okay, I have B, its predecessor was C, its predecessor was S. So this is the shortest path, right? It turns out this is Dijkstra's. Um, so I won't write out the full pseudocode. I'll just kind of describe it. And then we'll talk about the negative weight thing. Um, initialize a table of, if there was the same weight, would both paths be stored, or is that implementation dependent? If it's the same weight, you can do whatever you want, right? If it's the same weight, then S to C to B and S to A to B are both the same, um, both have the same weight, right? So you can overwrite it or you can leave it. It doesn't matter. You return it. That's why you say A shortest path, not the shortest path, right? So we start by initializing a table of distances. We'll say the distance to S equals 0. The distance to everything else is, we'll mark it as infinity, right? Then we say in BFS order. Actually, here we want to do something a little bit better than BFS, right? We want to say in um, increasing order of distance from S. Check all V to U and update the distance to U. If we updated, put U in the queue, right? Read. If we updated, put U in the queue and update predecessor, right? And then we just read off the path at the end, right? When I say a queue, we want things to be in increasing order of distance from S. So in fact, this is going to be a priority queue, right? So really what we're doing is we're initializing S to S, this distance is zero. Sorry, this is the predecessor. We're initializing this distance as zero, and then we have a priority queue. We put S into the queue. Then we dequeue from the priority queue, look at all of the neighbors. We dequeue a vertex from the priority queue, look at all of the outgoing edges, and try to update the distance to all of the like destinations of the outgoing edges, right? And if we've updated something, we put that into the priority queue, and then we dequeue and we sort of keep going, right? Now, the thing about negative weights here is if you ever have a cycle with a negative weight, right? So like this could be like -5, for example, right? Instead of 10. And then this would be 7 plus 4 is 11, minus 5 is 6, right? So that would give us a distance from S to S of 6. That's not better than 0. So who cares? We don't update. But if this were like a -4, right? Now all of a sudden we've got a cycle with a weight of 7 minus 4 minus 5 is -2, right? This is in fact nonsensical because any like any path that we take, we could always go once around this loop and make it shorter, right? Like we have a path of length 12 from S to C to T, right? This is a length 12. I can make it length 10 just by looping around here and picking up a -2. But why stop there? I could loop around twice, pick up a -4, and make it 8, right? I could loop around 6 times, rack up those like a -12, and then take the path to get a total length of 0. Or why stop at 6, right? I could do 100. I could do 10 million. I mean, it's nonsensical. But in general, if you have a negative weight somewhere, um, there's no reason this shouldn't work, right? In the sense that you can still like relax a path as long as you don't get a negative weight cycle. So that's Dijkstra's. Um, I realize we didn't talk about A star, and it's 9:43. So I'm gonna stop the recording here.